go ahead and get started, and well, we'll see what goes. Okay, you remember last time, let's get, last time we just started into chapter 4 and talked a little bit about propagation and stuff. Now we're gonna go a little further into that. We're gonna talk about antennas and feed lines and just a little bit on test equipment. And Mike, am I sharing? Is my screen sharing?
Yes, you are.
Okay, good. Um, like Jerry says, and it's such a great description. What you get for the technician exam is we cover an area that's a mile wide, but only 1 inch deep, So there are some uh, there are some of these subjects that you could do a college major in. And especially like in chapter 3, that's there are electrical engineers who spend all their time with, going into depths with electricity and electronics, but you just get a little thin share of it from us. Okay, so tonight we're going to talk about, all right, let's talk a little bit about antennas. And and let's see if I have that. Let's see if I have that cool graphic up. And no, of course I don't. All right, well, that's okay. Okay, I'm back to sharing, yes?
Yes, you are.
Okay. So antennas, the antenna is that cool part. And you know what? I think Jerry just joined us. Let me take just a minute and make sure Jerry is set up.
Jerry is not set up, I'm afraid. I don't see a picture. Shucks. All right. Let me check out and check back in.
Okay, fine. Jerry?
Yeah.
Here's the way I thought it would go tonight. I'm probably going to take a bunch of time tonight, so I kind of thought you may want to hold off for chapter 5 until next week.
That's fine.
Okay, because I think I'm going to take up a bunch of time, and maybe not the whole 2 hours, but if we get to the end and there's only like a half hour left, well then it's probably better just to hang on. Okay. All right.
Okay, real good. Okay, real good.
And Jerry, are you gonna? Where's participants? Jerry, are you going to get out and get back in, or what? Apparently, he is.
I think he did.
I think he did. Okay. All right. Well. Okay. So the antenna. The antenna is that piece of your system that creates the radio wave. In your radio, what you're doing when you're taking a signal is you're creating an electromagnetic wave, and that electromagnetic wave travels to your feed line or your cable, and from there, let me see. Okay. So your radio creates an electromagnetic wave. The electromagnetic wave goes out to your cable, which takes it out to the antenna, and from the antenna, it radiates a radio wave. And the radio wave is what travels through space until it hits someone else's antenna, and their antenna captures the radio wave, feeds it down into their cable, and it becomes an electromagnetic wave again, and their radio then decodes that and turns it into well, if it's speech, it turns into something you can listen to, or if it's data, it turns into something you can record. Okay. Oh, and the feed line, we talked about the feed line. That's your cable that connects your radio out to the antenna. And then we'll talk a little bit about test equipment and matching equipment in a minute. Now, all right, we're going to talk about some pieces of an antenna. An element, which is just a part of an antenna designed to either send out a wave or receive a wave. There's a driven element, which is actually supplied with power from the transmitter. And when they talk about arrays, they're just talking about antennas with more than one element. Now, they say parasitic element, resonance, and okay. Here, let's do this. Okay, can you all see me? Okay. Now, can you see this?
We can.
All right, this is an antenna. All right. Now, what they're talking about, in that last slide, they said, oh, there's a driven element in the antenna. And that is, for instance, can you see this here? This is where your cable connects. And your cable is then electrically connected to this one element. Okay. You see, I've got 1, 2, 3, 4 elements, but only this one, the driven element, only this one is connected to your cable. These others are referred to as parasitic elements because they're not connected to your power. Now, in the front of your antenna, maybe I should do it this way. In the front of your antenna, you have directors. If you're broadcasting, this is the direction you're broadcasting. This is the front of the antenna. When you're receiving, the radio wave comes in this way. It gets to here. Back here, this back element, this is a reflector, okay? And someone who's really, really smart can tell you how all that stuff works. Okay.
Is that a directional antenna?
That is a
what you're saying?
directional antenna. It's also sometimes called a Yagi, Y-A-G-I. And the Yagi antenna, it's named after a Japanese guy, one of 2 guys who invented it. While I've got this, let's talk about, later on in the book, it talked about polarity. Now, you remember when we were talking about radio waves, we said that the radio wave is made up of 2 waves, an electrical element, an electrical wave, and a magnetic wave, and they are at right angles to each other. Now, when we're talking about polarity, what we're talking about for direct line communication, short range communication, it's best if you're sending out on a vertically polarized antenna, the person trying to hear you will do best if their antenna is also vertically polarized. Now, when we're talking about vertically polarized, we're talking about the direction of the electrical wave, not the magnetic wave, the electrical wave. Okay? So now in this case, you see I've got my elements perpendicular to the earth. So this is a vertically polarized antenna, and it's good for that. Now, so in chapter 4, it also told you somewhere back toward the back of the book that, toward the back of chapter 4, that if you're trying to do single sideband on, for instance, 2 meters on VHF, that and trying to do distance, it's best for you to have a horizontally polarized antenna. Well, this is vertical, so what I would have to do to make it horizontal, I would have to change my little elbow joint here and mount the antenna like this, so that the elements are parallel to the earth. Okay? All righty.
So Bob,
Let me also show
have a-
this too, if you don't mind, Bob.
Oh, go right ahead. Yeah.
I like making antennas. So
Okay.
that was a directional Yagi. And that looked like it was a 2-meter antenna, right?
Yes, it was.
This is a 23 centimeter. Do we do? Let me. I got another one here. Where did I put it? Where did I put it? I have a 70 centimeter here that I just had, and I don't know what I just did with it. Shoot. Oh, here it is. So this one is 70 centimeter. I don't know if you can see can you see the whole thing? I can't see.
Yes.
From this back.
Yes, actually.
So you can see how long the elements are. This is 70 centimeter. And this is just made out of just copper wire, house wire. I had some old pieces of house wire, and I'll go back to this 23 centimeter one. This is your direct element here. The feed line would connect here, and then these give you this is your ground plane for the antenna. And so this is the position that it would be in when it was in use, with it pointing straight up and down. These antennas that I've made, these ground plane antennas, were the first antennas I made. And I was amazed that out of a coat hanger, I made one. This you probably recognize as a telescopic antenna that you've seen on a transistor radio at some time in your life, probably. I have done the exact same thing as this, using these. And you got to be careful when you do it because they need to be short enough. This one is a little bit long, but I have some other ones that are a little bit shorter. When they're all the way in at 70 centimeter, and then I can pull them out to almost all the way out, and it's good for 2 meter. So it's you can use it on both frequencies.
Okay.
So it's really great, for you can make your own stuff and not have to spend a lot of money. The only thing I spent money on is the piece that screws into, it screws your feed line into. It's just a surface mount. It's called the surface mount. And they're a couple of dollars on Amazon.
Yeah.
And so you don't have to spend a lot of money to make your antennas. And then I just, put this on a piece of, a 15-foot piece of PVC on a little tripod outside my window. And I'm talking to everybody on all the repeaters in the area. It's amazing what you can do with just little stuff like that. That Yagi that Bob showed, did you make that, Bob?
No, you know who did? Hugh, K-E-8-B-E-D.
Okay, so I've also made a couple of Yagis because I wanted to get into talking to the space station.
Yeah.
And so those are great for that because you're directional. You can follow it and be pointing right at it. This isn't going to be as good for talking to satellites because they're moving too fast across the sky. Yeah. And
Okay.
so you want to be able to be directional and follow it as it goes. So that's it. That's it. I just wanted to throw that out there, Bob.
Okay. Okay, let me pick up Chris here. Christopher, you had a question?
Yeah, so regarding what you had mentioned about polarity with the Yagi, for example, does that also apply to, like, say, a handheld radio? Like, say, I'm talking into it like this, but then somebody else is holding their radio like this. Could that potentially mess with, I guess, the distance, quality of the signal?
Yes,
Yes,
yes, it can. In fact, you know what? There's kind of a funny story. There's one guy who's down in Oak Park, and sometimes he calls into our Sunday Night Net using his little handheld, and sometimes he's got a good signal, and sometimes it's not good at all. And I told him one night, you're just all broken up and you're staticky, and it's not a good signal. And he said, okay, wait a minute. And then he called back in a minute, and his signal was pretty good. I mean, he's only about a mile from the repeater site anyway, so he should have a good signal. But you know what made his signal better? He had been sitting in his lazy boy chair on full recline. So in other words, his antenna was pointing horizontally. And so what he did is he just sat up in the chair, and so he's then vertically polarized, and we're good to go. So
Good to know. Okay, so it's like that with pretty much any antenna then.
okay, now wait a minute. Now we're talking specifically about VHF and UHF. When you get to the lower bands, the lower frequencies, your radio signal is going to be bouncing off the ionosphere. And when it does that, whether you send out a vertically polarized signal or a horizontally polarized signal, once it hits the ionosphere and kind of bounces back, it comes back as an elliptically polarized signal. And you can pick that up with anything, So on the HF bands, below 30 megahertz, especially when you're going for distance, then the polarity isn't as big a deal. But when you're on 2 meters and 70 centimeters and you're doing line of sight communication, it matters. It matters very much.
Bob, do you have sharing on?
Yes,
Okay, can I share something?
you certainly may.
Thank you. Let's see if I can do it.
Okay. Yep. We see you.
You see me. Let me see if I can get the
Zoom.
But
paste and go. Okay. This is the Livonia Amateur Radio Club. They're in a park on a Saturday. This is a Yagi antenna. Actually, it's 2 Yagi antennas. The longer one is cut for 2 meters. The shorter one is cut for 70 centimeters.
QR, is that what was the call sign again? Okay, there we go. November 1, Queen Delta Queen. Okay, thanks. I'm in Echo November 82 giving a satellite demonstration for the radio club here at QSL. Okay, FM 401 Southern Rhode Island. Okay, great. Well, thank you very much for the contact. Yeah, once we get off of here, we're going to go down Greenfield and try to demonstrate what that looks like.
Okay, there you go. That was using a directional antenna, the Yagi antenna, directed to a satellite that was going by. We have programs that will tell you where any particular satellite is going to be, so you can if you're in range, you know where to aim the antenna. And the Yagi antenna is not ideal because of the polarity, actually. But Bob will tell you a little more about polarity afterwards. Thank you.
okay. Okay, and let's view speaker view. Huh. Well, that didn't work. All right. Oh, Jerry, did you stop sharing?
Yes.
Okay. Well, for some reason, that's all right. Mike was talking about having made antennas. You know, that's one thing. If you're cool with this stuff, this one little part here, where the coax connects, the guy who built this, he had to buy that one little part. It was about $5. All the rest of this is made out of scrap material. The PVC was stuff he had lying around. These are parts of an old, I think, television antenna that he just, cannibalized for this. So with skill makes up for a lot of money. Okay.
Amen to that.
Yeah. Yeah.
Actually-
Brains and skill make up for a lot of money. Okay.
There's a little project that some clubs do. Instead of those old TV elements, you can actually go to Harbor Freight and buy yourself a long tape measure and cut off strips of tape measure. That way you can make the element, and when you're done, it rolls up.
Yeah. Yeah, that was going to be my next Yagi, actually, because I think that's a pretty cool idea to make a Yagi out of tape measure. I think that's wicked cool.
Yeah. Okay. All right. Where am I?
And while you're figuring where you're at, Bob, just one last thing, just so everybody knows, the satellites and the International Space Station and anything up there that you're talking to, those are all pretty much going to be talking on 2 meter or 70 centimeter. So you will be legal to talk to just about every satellite in the sky that has a radio on it.
Okay. Radiation. I thought they covered that point in chapter 2. Radiation. It's not radioactivity. Yeah, no. What we have in radio is non-ionizing radiation. So, don't worry about your genetics. Your grandchildren will be just fine. Okay, we kind of talked about the radio electromagnetic waves. Yes. Oh, yeah, I kind of been through all that. Spoiler. All right. Vertical and horizontal. Yes, determined by the elements. We kind of been through that. Circular orientation. I think a lot of the communication that comes down from the satellites comes down as circular circular polarity. And then, of course, as I mentioned, elliptical polarity. Yeah, once you start going in the lower frequencies, in the HF frequencies, you're going to bounce your signal off the ionosphere, and it's going to turn into an elliptically polarized signal. And you can receive that with either horizontal polarization or vertical polarization. And I'm sorry, someone did have their hand up, and it kind of went down. Jeremy, was that you?
I did. I don't know if I cut somebody else off. My question was, if I go horizontal, so with the directional vertical, I get that I can turn it. Horizontal, do you go up and down, or is it always flat?
Horizontal, the elements for horizontal, the elements have to be parallel to the earth. Okay. For vertical, it's going to be perpendicular to the earth.
So even when you're talking to the space station, you don't aim it?
Well, Bob, you grab your Yagi again.
Wait a minute. See, the thing is, when you're talking to the space station, you're actually going to be pointing this You're actually going to be pointing it in the air.
Okay,
Right.
right, okay,
Okay, you're going to be, yeah, you're going to be pointing this up in the air, and
Okay.
and it's going to get up there, and I think they're going to receive it as circular, but I'm not sure. Don't quote me on that. Okay.
And as far as like I guess circular, like is that sort of like what you would get with one of those round satellite dishes, like if you had like Dish Network or something like that, or is that something different?
That is a good question to which I don't know the answer. Jerry, can you weigh in on that?
Are you on mute, Jerry?
Jerry is on mute.
Yes, that is a good question, and I'm not sure the answer either. With the dish, actually, what's happening? The radio waves are bouncing against the spherical part of the dish and focusing into the receive element is actually above the center of that dish. So all the radio waves that are going in there are being collected and sort of focused into the receive element. And
reflected back to
sounds like, yeah, sounds like it's a circular orientation. It seems like that to me.
Sounds right.
Now, the thing is, well, again, we're always going to say this. Theoretically, everybody should have the correct antenna. Now, if you're operating on the 80-meter band, your antenna should be 132 feet long and probably at least 100 feet high. Nobody's going to do that. You got to do what you can.
right.
Okay.
One other thing is as far as conventions on VHF, UHF. If you're going to use FM and digital, you're going to generally use a vertical orientation. The repeaters have vertical antennas. The whips on your car are vertical. If you're going to start doing what they call weak signal, like Bob's Yaesu 991 does both sideband and FM, even up in the VHF, UHF areas. If you do sideband and code and some of the digital on VHF, UHF, you're going to use a horizontal orientation, but the vertical orientation is for the for FM. Go ahead.
Okay. Now, like we said, what we're teaching you here is to pass the test. The subject matter is a mile wide and an inch deep. And that especially goes for this next topic here, the decibel. Decibels. All right. Here's what I want you to remember, okay? I want you to remember three numbers. 3, -6, and 10. 3, -6, and 10. There are only 3 questions in the question pool that deal with decibels. And the answers are either going to be 3, -6, or 10. Now, on the question, on 2 of those questions, only one of those numbers will appear in your multiple choices. All right, so, but on one of those questions, they're going to give you 2. We'll get to that later on, but just get used to thinking of the decibel questions as having answers of either 3, -6, or 10. Now, for those of you who are excited by mathematics, you can go on and go into all kinds of detail about this, about logarithms. I remember in high school, I think it was Algebra 2, and I liked logarithms very much. However, that was 1964, and what I remember about logarithms is virtually, it's just kind of vague. But you can get past your technician exam. And remember, that's what I'm trying to do here. I'm trying to get you past the technician exam. And you don't need to know great levels of detail about that. Okay. Now, okay, some interesting gain. This is an important topic. If you have, let's talk about this second term, an isotropic antenna. Isotropic. There is no such antenna in existence. If there was, it would be a single point that radiates its energy out in all directions equally. Okay. The theoretical, it's a theoretical concept, and it's a theoretical concept used to determine the effectiveness of other types of antennas. Okay, because the isotropic antenna, since it sends all of its energy out in a like a sphere, it's sending it out to directions you want to go and directions you don't want to go. Okay, now the Yagi antenna, the directional antenna, will take all of your power and send it out in one direction. Okay, and the amount of improvement, the increase in apparent power, is referred to as gain. The thing you need to remember is if you have a 50-watt radio, a 50-watt transmitter, using a directional antenna, you're not going to get any more than 50 watts. It's just that using a directional antenna puts all those 50 watts going in a single direction. It focuses the power so it can go further. All right?
I can appeal to the little boys in us. When someone first gave us a magnifying glass, we would go out in the backyard with it on a sunny day and concentrate the sunlight and be very mean to ants and stuff. That's what the antenna gain really is.
Yeah, right. Yeah, the sun doesn't get any hotter. It's just that its energy is focused. Okay. Omnidirectional. As you start off as a technician, for many of you, what you're going to start off with is a vertical antenna. All right. And a vertical antenna is going to send out its energy in 360 degrees, but not like the isotropic, which sends it out, spherically.
Oh no, the vertical antenna is going to do it spherically.
Yeah,
really.
the vertical antennas, they don't send so much down.
Right, that's right. That's true.
Yeah. So, because the vertical antenna, and Jerry, you told me this a while ago, the vertical antenna actually has gain. And, because I always thought the vertical antennas wouldn't have gain, but they do have gain over an isotropic antenna.
Yeah, I think the isotropic antenna was a plot made by the antenna manufacturers. I'll tell you why. Before this isotropic thing was invented, probably in the 1970s, we used the dipole to compare the gain of a Yagi or whatever other kind of antenna to a standard antenna. The standard antenna was the dipole. The isotropic is less efficient than a dipole. It's 1.3 decibels lower or something like that, or is it less than that? Or is it less effective than that? What does your book say?
I don't remember. I thought the vertical antenna was something like 2.2.
Oh, okay.
It had a 2.2 decibel gain over an isotropic, not over a dipole,
Right.
over an isotropic.
Okay, later on, when you talk about different lengths of antenna, a lot of people get what they call a 5/8 wave antenna, especially if you're handy-talkie. That's known as the poke your eye out antenna because it's longer than a regular vertical. But what that does, because of the length, the radiation is different. Instead of a perfect sphere, it gets kind of squished down. The top goes down, so it almost looks like a donut. And when it's squishing the top down, it's making the middle go out farther. So the 5/8 wave actually has gain over a quarter wave vertical.
See, okay. All right. Now, while we're talking about gain, first off, this is a radiation pattern that shows you how an antenna is sending out its power. Now, this is what's called an azimuthal pattern, and I'm not sure I pronounced that right, but anyhow, something like that. And this is the pattern as seen from above. You know, if you were looking down, this is what, if you could see the radiation pattern, this is what you would see looking down on it. Now, what this shows is over to the far right on the x-axis, that's where most of this radio energy is going. It's going in that direction. Now, on the next slide, they're going to start talking about things like measurements of effectiveness. And one of those measurements is the ratio, the forward to back ratio. So that's the ratio of how much power is going in the direction you want it to go, as opposed to how much power is going directly behind it, 180 degrees behind it. And obviously you want a very, very large forward to back ratio. Now there's also something called a forward to side ratio, and that's the ratio of the power going forward to the power going to 90 degrees, or at right angles, let's say at right angles. So it's 90 degrees and 270 degrees from the origin point. Okay, and that measures how much radio power you're losing out to the side. Okay, oh yes, and it's graphed in decibels. Yes, yes, yes. Oh, nulls, lobes, main lobes, side lobes. Oh, we can talk about this stuff, but it's better if you see a picture. All right. Now, over on the left here, you see that's the azimuthal pattern, radiation pattern, as seen from above. On the right is the elevation pattern. Now, this is the radiation pattern that if you could see it standing to the side of it, not on top, not to the top of it, but on the side of it. Now, again, you're trying to shoot your power out to this main lobe, out to the right. And the thing is, there's some of these areas where you get nulls, which actually is good, you know, because the nulls are particularly good if you want to hear something from this direction and you don't want to hear the interference from, you know, nearby or stations, you know, nearby. Okay, so this would be the main lobe. This is the side lobe, which is, you know, 90 degrees to the, or at right angles to the main lobe direction.
No.
The main lobe direction.
Now, Bob, you can see that the the main lobes are at a sort of angle towards the ground, and with HF if you can find an antenna that has the lowest angle to ground, then it shoots the radio waves farther into the ionosphere, so they will bounce farther.
Mhm.
So
Yeah.
vertical antennas have a habit of having low angles of radiation in the elevation pattern, and that's why a lot of people go for them.
Okay.
Aside of the fact that they take less space.
Yeah, and you get, you know, the nice takeoff angle, the lower takeoff angle.
Mhm.
Okay. All right. Oh, front to back ratio, front to side ratio. We told you about that. All right. Basic
But,
feed.
before you get into that, can I make one other observation, Bob?
Sure. Do you want the picture?
No, it doesn't matter. Well,
Okay.
with the Yagi antenna, you're going to go well, go in a certain direction, and you aim your antenna. For instance, I can aim my antenna to an area in France, and the maximum amount of power is going to go in that direction. The maximum amount of receive ability is going to come from that direction, and that's all well and good. Suppose I'm on 20 meters and I call CQ, and I get two stations answering me, one in Rhode Island and one in San Diego. I'm going to hear the guy that I'm aimed at. I'm not going to hear the other guy very well if I'm not aimed at him. So it's sometimes pays to have an antenna that can radiate and listen in more than one direction. That's what I'm saying. Dipoles go in two directions, so that sometimes helps.
Okay. Okay, and we've now feed lines. Feed lines are fun. Normally, what you're probably going to start off with is coaxial cable. Let's get a picture here somewhere. Oh, center conductor, dielectric, yes, yes. Words, words, words. But let's have a picture. Okay? All right, the center conductor, that's what's carrying your signal. All right, and your signal actually travels on the skin, not through the center, but on the skin. Then there's a dielectric, an insulator, and then an outer braid. All right, and then of course just an insulating jacket, a protective insulating jacket. What they're showing you down here, and this looks like I don't know, maybe RG58 or something like that.
Sure looks like.
Yeah, in fact, let's see. The thing about this, well, here, let me show you this. Okay. Can you see this? This is
Back just a
RG.
little bit, Bob. Pull
Sorry?
away just a little bit. It's blurry. Pull back. There you go.
That's
There
better.
you go. Yep.
Okay. Can you see the actual wire, the actual?
Yeah.
Okay.
That's fine.
All right. So that's it. This is one type of coax. It's RG58. Very cheap, very easy to use, very, very flexible. Since it's got this, well, I've got the braid kind of bunched up here. And I did that because a lot of times in connections, you're going to connect the center conductor to one point, and then the braid you're going to connect to another point. But anyhow, since the rest of this is shielded by braid underneath the plastic covering, you can actually run this along gutters, so because it kind of protects the what do you call it protects the electromagnetic wave inside, you know. All right, so this is that. Here's a tougher kind of coax. Is that okay?
Yep.
This
Looks like RG8 or LMR 400.
Yeah, this is LMR 400. Now, this is very, very low loss. This can be used on VHF and UHF very effectively. However, this RG58 is very cheap. This RG8, see,
It's
it's a
almost the
bit,
same.
yeah, it's a bit thicker, but also very, very flexible and has less loss for its length.
Mhm.
This is even better, but this is very stiff and it's tough to work with because you can't do lots of bending and whatnot. You can bend a little bit, but over length, but it's very, very stiff, very strong though, and carries signals very, very well.
Unfortunately, the RG58 is not very efficient on VHF, UHF.
Yeah.
You lose a lot of power as it runs through the coax. So some people, if you have a long length, 100 feet or something like that to get your antenna, then it might be worthwhile to bite the bullet and buy the thicker one.
Yeah, the LMR 400, it's very, very good, but it's about $1.25 a foot. So, yeah.
Okay, if I can be a little sacrilegious,
Okay.
if you meet a friendly cable guy who's doing some work and maybe getting rid of a whole bunch of old cables and stuff like that, the cable TV stuff looks like our RG58, but it has a different impedance. However, it's close enough so the losses you'd suffer won't be that great, and free is better than nothing.
Amen. Okay. So, okay, that's the skinny on coaxial cable. There are other types. There's what they call either twin lead or window line,
Or ladder line.
or sometimes called ladder line. And the thing about this is that they're very flexible, they're very easy to work with, but they're not shielded. So you cannot run this along your gutters. You've got to be careful what's in the neighborhood, what's real close to it, because it can metal can interfere with your electromagnetic wave. Okay, and like they say, yes, it's lighter and less expensive, has lower loss at most frequencies. They say, yeah, more difficult to use because it's affected by nearby materials. And since you get out to your antenna may well be 50 ohms, and this is, either 300 ohms or 450 ohms, you're going to need, another little piece of equipment to go in there.
And actually, Bob, for my wire antenna, I do use the window line, and that works pretty well. And I don't have to worry about losses, about it's eating up my RF power. But I run it up. Well, when I was 50 years old, I was able to get up into the attic and put a lead from my Radio Shack all the way out to the side of the house and put insulators and stuff like that. It's quite a bit more labor intensive to put it in, but if you can do it, it's worth it.
Yeah. Yeah. There's that trade-off, cost versus convenience. Okay. Yeah, and here's what they're talking about: impedance traveling through the feed line. When in this, you see, you got 300 ohm on the twin lead and 450 ohms on the window line.
People used to make those out of wire and popsicle sticks as the separators.
Yeah,
Huh, huh.
yeah, I'd seen that. Hmm.
You boil the popsicle sticks in paraffin wax first.
Why?
Weatherproof.
Oh,
Yeah, it's something from rotting.
Yeah.
oh, okay. All right. Okay. But that's all well and good, but again, you've got to deal with the difference in impedance. Okay.
So we've
Standing
talked
wave.
a little bit about, cheap stuff. You can scour the internet, like I did. I decided for one of my antennas that I was just going to try, and I spent extra money. There's a company in Italy called Massey and Poloni, who supposedly, from looking at their specs, makes some of the best coax cable. And it's a little expensive, but losses are so low. They make some really great cable. So if you want to spend the money and make it easier, you can also spend money and make your tasks a little easier. So that's just the other end of the spectrum.
And
Okay.
of course, wait, there's one other thing. I think there's a question on it, isn't it, Bob? About using hard line. I know we use hard line for our repeater, and that uses either air or some sort of inert gas as the insulator instead of polystyrene or whatever they use.
Mhm.
And that's very hard to work with and very expensive.
Yeah.
So unless you, I don't know, I'd rather spend it on champagne myself.
Okay. All right. All right. Let's see. Um, okay. Standing wave ratio. This is a big deal. I found this this video. It's just a few minutes, but I think it's worthwhile. Okay. Standing wave ratio is, from your radio, you send your signal, your electromagnetic wave, out to your antenna. If there's not a perfect match, a perfect impedance match between your feed line and your antenna, then some of that power is going to get reflected back to you. It's not going to make it to the antenna. And when it's reflected back to you, what's that going to do? You're going to lose the power. You're going to lose it in terms of heat, and it's going to go back to your receiver set. Okay, let's see if I can get this going.
VSWR, or voltage standing wave ratio, crops up in a variety of areas associated with radio frequency technology. What really is it, though? In this video, we'll explain what VSWR is and how it arises with the help of some diagrams and animations. And then we'll look at some of the key equations, so you'll have a really good understanding of what it is. First of all, let's start with
I'm going to stop it when it gets toward the end and they start talking about the equations and the gamma figures and all that. But this first part, it is worthwhile for you to see.
Basic explanation of VSWR. Within a radio frequency environment, power is transferred from one point to another using a transmission line or feeder. These feeders may be a variety of forms. They may be two parallel wires known as a twin or open wire feeder, or more commonly coaxial feeder or coax for short. Other forms of feeder may also be used, but essentially they all act as feeders. These feeders are said to have a characteristic impedance, and the maximum power transfer occurs when the feeder transfers power to a load having the same impedance as itself. Similarly, the maximum power transfer into the feeder occurs when the source has the same impedance. If we have a 50 ohm feeder, say, and a 50 ohm load, then all the power is transferred from the feeder into the load and everything's fine. If there's a mismatch where the feeder impedance and the load impedance are not the same, then it's not possible for all the power to be transferred, and the
Okay, and the load they're talking about, that's your antenna. That's the working part. That's going to send out your signal, okay?
remaining power does the only thing it can and travels back along the feeder as a reflected signal. And where the feeder is a reasonable proportion of a wavelength, voltage and current standing waves become apparent, as we shall see later. Let's see how this works out. If we have a perfectly matched load as we have here, the power travels along the feeder, and we can see the voltage waveform here. As we have a matched load, all of the power is absorbed and none is reflected. There is no reflected voltage waveform. This is the ideal case for most applications. Now let's look at the case where a short circuit is applied to the end of the feeder instead of a load. Here we see the voltage waveform moving forwards to the load, or in this case a short circuit. At the end point, the voltage must be zero and power is reflected. A reflected voltage waveform is seen, and the overall voltage at any point along the line is the sum of the forward and reverse voltage waveforms. It can be seen that the voltage is always zero at the short circuit point, but it rises to a peak of twice the forward voltage further back along the line, but more of this later. Similarly, if an open circuit is applied to the end of the feeder, the voltage waveform moves towards the open circuit, and again power is reflected. The current is zero at this point because it's an open circuit, but the voltage rises to twice the voltage of the forward waveform, with troughs and peaks back along the feeder. Where do these peaks and troughs occur, and what do the plots of voltage along the line look like? For example, let's take a look at the case of the short-circuited line. Here we see the voltages arising from both the forward and the reflected power again. As the power is reflected, we see the combined voltage at the short circuit is zero. But further back along the line, there's a point where there is a peak. If we make a plot of the combined voltages and currents of a short-circuited line, we see a plot like this. The shape is quite distinctive, looking a little reminiscent of a set of half sine waves joined together. We also find that if a much smaller mismatch is applied, the plot looks almost sinusoidal, as we see here. Then, for an open circuit line, we see a similar set of waveforms. The voltage resulting from the combined forward and reflected power is at a maximum at the open end of the feeder, whilst the current is zero. And likewise, for a smaller mismatch, where the impedance is above that of the feeder, we see the plot reminiscent of a sine wave again, with the voltage being higher at the point of the load. It's also worth realizing that there are no power standing waves. Power is reflected from a mismatch, and there's forward and reflected power. These are constant in either direction, assuming no losses. It's the voltages and currents from the forward and reflected power that combine together to set up the voltage and current standing waves, as we have seen. Now we can define the voltage standing wave ratio. It's the ratio of the peak voltage along the feeder or transmission line to the minimum voltage. It varies from +1 to infinity, and it's always positive. It's typically given as a ratio like 2 to 1 or 3 to 1 or even infinity to 1, and a perfect match is 1 to 1. It's also possible to look at the VSWR in terms of what is termed a reflection coefficient. This is another ratio, and it's the ratio of the reflected wave to the incident wave.
Okay. We don't need to get into reflection coefficient. That's never covered in the tech class, and as a matter of fact, I don't remember reflection coefficient even being covered in the extra class. Okay, but that gave you the idea, I hope, that this is, standing wave ratio is kind of a big deal. All right, let's get back to wait a minute.
If I can share something, because this is what you're going to start talking about.
Okay, go ahead.
Okay. Standing wave ratios, SWRs and antenna tuners and the like, have become an obsession. And you'll find all sorts of discussion groups discussing how to get it down to 1-to-1. And you don't have to. You don't have to. Just think of it as a voodoo discussion. Okay, Bob.
Okay. All right, back here. All right. All right, so the whole concept of standing wave ratio is that when you have a mismatch between the impedance of your feed line, your coaxial cable or your ladder line, whatever, between that and the antenna, then there's a mismatch. And when there's a mismatch, the power cannot get completely to the antenna. And since it can't get to the antenna, it doesn't just disappear, it has to go somewhere. So the power that doesn't get to the antenna gets sent back to your receiver. Now, what happens is it's going to get rid of that energy, and it's going to get rid of it in terms of heat. And you know that going back to your the power going back to your receiver is not a good thing. Most modern radios are going to have circuitry in it that when it starts seeing a big mismatch, when it starts experiencing a big mismatch, it reduces the power that you're sending forward, so that of course it gets less power is reflected. You know, at some point, you know, your 50 watts you're sending forward, you know, if you have a terrible mismatch, it may be cut down to, you know, 40 watts or 25 watts. There's actually a table somewhere that I saw that, but I didn't bring it in. We don't need it. But yeah, you're going to be reducing the power sent out, and at some point, you know, you can actually end up hurting your rig. Okay.
Hey, Bob, I got some question.
Yeah.
When going back to the coax and stuff and the reflected power, you've got your coax, you've got your transmission line in the center going out. So that reflected power, is that coming back through the shield? Is that what that does? Or I'm not exactly sure what the role of the shield is, unless it's for power going back or used as a ground, or what the purpose of the actual shield is, if not to absorb that reflected power coming back.
The big function of the shield is to protect the wave going through the center conductor. So,
okay.
So what it does is it serves to isolate it from the surrounding. So that's why you can run coaxial cable along your metal gutters, but you can't do that with ladder line, because ladder line doesn't have a shield on it. So that's the big thing. As to whether the reflected power comes back on the shield, I don't think it does. I think it comes back on the center conductor.
Yeah.
I'm not sure about that, but
It would seem strange that it would go out the center conductor and be able to come back also.
Well, Bob and Mark, what you have going through the coax is still electron flow. Very exotic electron flow, but it's still electron flow. It doesn't become a radio wave until it gets to the antenna. That's where the conversion is. So, and you're talking about alternating currents. So, you have to have both the center conductor and the shield.
Yeah, going back and forth.
Right, to make a circuit.
Right.
Then once it gets to the antenna, then the radio wave takes flight.
Okay. Thank you.
okay.
So just to put this a little bit into perspective, Bob, if I can. So if we go back to this little 23 centimeter antenna, when I made this, I made these pieces about 10 centimeters longer than I needed to. And then I hooked it up to my meter and saw what my SWR was. And we call it SWR. It's really VSWR, but no one says that.
No one says
Don't get confused when
Yeah,
you
it's
don't see the
SWR.
V. The VSWR and the SWR are exactly the same thing. But so then I hooked this up to my meter and looked at what it was, and I trimmed a little off of them, and it got closer, and I trimmed a little more off, and it got closer, and I trimmed just a little more off. And this particular antenna ended up being 1.07 to 1. So this is almost perfect, which was a huge surprise to me, but I'm pretty proud of that. But so just to put it into reality, how easy it is to match, an antenna like this, it just by trimming a little bit, it's hard to add. You can, it's hard to add. So when you're making your antenna, you always make them long and then trim them back. But so just wanted to throw that little practical piece out there.
Mike, I hate you. You're too perfect. I always had to add antenna stretchers.
Jeremy, what you got?
So I do have a question. Why does, so I'm only a CB guy. I'm not a ham guy yet, but why is it when I'm trying to tune my CB antenna with an SWR, they say they want me out as far away from every buildings, trees, things like that when I'm tuning it? How does that affect the signal, like getting bounced back or what? I would think everything would absorb it, wouldn't it? Would the buildings and stuff absorb it, or do they actually feed back when they're doing that?
Jerry, you want to take that one?
The other stuff will absorb or detune. If you get too close to, say, a panel truck while you're doing your tuning, the metal in that panel truck may be doing a little absorbing of your radio wave, or making the antenna seem longer than it is, so you trim too much off.
I got you. Okay, that helps me out, because I was always like confused on why I need to be out in the middle of a field when I start trimming my antenna for the SWR. I was just curious.
Sure.
So your a CB is essentially 11 meters. So it's not going to be quite as it's not going to be as susceptible to interference from foliage as a UHF would be, but it is susceptible to impact from metal objects specifically. Yeah.
Yeah, I'm still holding a grudge because back in the 1950s, they took the 11-meter amateur radio band away from us and gave it to CBers.
Yeah.
The nerve of them.
The nerve.
Well, the chiropractors also had a device called a diathermy machine, which worked on 27 megahertz. I don't know if they were taken away either.
Anyhow, so CB, actually the antenna that I use for 10 meters, 12 meters, and 15 meters, it's actually a CB antenna. So, actually for 11 meters, but it does just fine on 10, 12, and 15. 20 is out of range. 20 is out of SWR, but 10, 15, and 20 works. Okay. Oh, and like Jerry said, you know what? Nothing is perfect. And it's like, sure, 1-to-1 is perfect. You're not going to get 1-to-1.
Right.
If you're below 2-to-1, you're golden. So, all right.
Bob, are we getting into the measurement of a dipole antenna and stuff like that? Instead of using 300 as as a coefficient, we use a different coefficient to throw in fudge factors.
Yeah, I think all that's covered in this chapter, though, is they talk about the 468, but then tell you instead start with 490
Yeah,
and
okay.
and work down. Mm-hmm.
Okay, yeah, it's a great Mackinac Island fudge.
Okay. All right. All right. Impedance matching. Yes. SWR. There's cool things that measure SWR. There, SWR meters. There's one right there. By golly. So, but if you have a high SWR, there's things you can do about it. There is something unfortunately called an antenna tuner, which does not tune an antenna. If you have a particularly high SWR, this device that's called an antenna tuner or transmatch, really all it does is it throws some additional circuitry in, so capacitors and inductors, and all it does is matches the impedances. Now, unfortunately, it matches the impedances back at your receiver, and it does not really change the mismatch.
Just to make the transceiver happy.
Just to make the transceiver happy, which is important. That's very important. But you still have the mismatch, and you're still losing some power. But
Yeah.
What the heck?
So Bob,
nothing's perfect. Nothing's perfect.
If you're running that antenna tuner in line, say in a mobile or something like that, is it okay to use that all the time? Or while you're working on your antenna, would it hurt? It doesn't hurt anything to have it running, right? Used in line, like in a mobile application or something where you have a little bit of a mismatch and fine tune it. Can you just leave it in line? And you
Sure.
run with it?
Oh, yeah.
You really wouldn't need, well, if you're using VHF and UHF, you can make enough adjustments, and the antennas are sort of broadbanded enough. You can make an adjustment just by, usually on an antenna, there's a little screw setting that you can unscrew and
Right.
let out or push in a little bit of length.
Yeah.
And that would tune your antenna a lot better than the antenna tuner would. So for
Right.
VHF, UHF, you generally don't need that kind of thing. And you can buy those magnetic antennas that are pretty much pre-tuned.
Mm-hmm.
You don't have to worry as much about that.
Okay. I just wonder if it was okay to run it and stuff. I would match the antenna myself by adjusting that,
Yeah,
especially for mobile, because I'm more going to be mobile beginning and turn it into a base with a big old Yagi antenna up there somewhere about 100 feet high.
Right.
About 100 feet long. That's what I'm looking at.
That
I
would be
love big
something to see.
antennas.
You won't make it under a single bridge.
Oh,
I've had that happen before with my mobile antennas. I had it too long and I was hitting the overpasses on I-94, so I had to angle it back down before I go in half.
Okay, well, one other thing about these transmatches or antenna tuners, there is a cost. They will absorb some power. So it's probably more efficient if you can adjust the antenna length yourself.
Yeah.
Right.
Okay.
Now, in saying that though, I have had experience that it does chew up your power, it does eat up your power, but will let you get signal out. My first contact in Europe was on somebody's Icon 7300 with an antenna tuner on it, with this with this little antenna, this little antenna that was probably only about 12 feet tall, sitting on the grass next to us on a little tripod. And I was talking to a guy in Europe, and it was like, I don't understand how we did that. When we removed the tuner, we couldn't talk to him. I could hear him still, but I could not transmit to him. So, while you do lose power, if you can't get it to match for whatever reason, I think the antenna was like 3.5 to 1 is how far it was out. And when we put the tuner on it, I don't know what it tuned it to, but it allowed us to talk to Europe. And I was like, holy cow.
Sure.
So,
you wouldn't,
but there is a cost in power,
Yeah.
you know, to keeping that in mind.
yeah, you wouldn't have 100 watts going to the antenna. You might have, 25 watts going to the antenna, but that was enough.
Right.
Right.
Okay,
So
and Chris has a good comment out in the chat, and the braid is basically like a little Faraday cage for external interference, correct? And basically, yeah,
Yeah,
it
you got
isolates the electromagnetic wave going through the center conductor, isolates it from the exterior.
Right. Okay,
Mike, when you were talking about talking to someone in Europe, was that only through Skip? Or like, did you have to bounce, or how did, like, just theoretically, how would that work?
You know, I don't know enough about how things bounce and how things work. This was a vertical antenna. You know, like I said, it was only like it was a ground plane antenna. So it had some radials, you know, it had 4 radials coming out from it, and it was only about, you know, 10 or 12 feet tall is all it was on this little tripod. And so I don't know how the bounce actually works. I don't know enough about it. If can anybody else, Bob or
Mike,
Jerry, can you
what
figure
frequency
that out?
were you on? Were you on the 10-meter band or the 20 meter?
14 meter.
14
I'm
minutes.
sorry,
So,
17 meter. 17 meter.
okay, well, 12 feet is actually, if you have that plus the radials of the proper length, what you have is a dipole antenna. That's cut for the 17 meter band. So yeah, that's pretty much it. It was a fairly efficient antenna. It had a low vertical, it had a low takeoff angle, and yes, it did skip a couple of times to get to Europe. Unless you're doing, you know, with a going through a satellite or something of that sort, you really can't get to Europe without bouncing.
Yeah, and so you may have bounced off the ionosphere and then off the ocean and then off the ionosphere again.
And the
who
ocean
knows?
again, and maybe France, who knows? Yeah.
Yeah, so. Okay, next, hey, let's talk about a really, really intricate piece of equipment, the dummy load. The dummy load. Let me show you what a dummy load looks like. Here it is. And if you say, well, that looks like a paint can. Well, yeah, pretty much that's what it is. It's filled with oil, and you know the coax. This is something if you're testing your radio, and you don't want to send out signals, you hook the radio up to the dummy load, and all the energy goes from that you're putting out from your transmitter goes into this can, which is filled with oil, and there's a great big resistor in there, and so you're theoretically, at least. Now Jerry has a funny story about that, but theoretically, at least, you're not bothering people by sending out, you know, test signals. Okay.
Sure.
So.
Well, my funny story is that before Heathkit came out with, which was the original Cantenna, came out with the resistor in a can of oil, we guys used to use a 100-watt light bulb on our transmitters as the dummy load. So we'd put that into the coax connector, and the light bulb would blink as we talked or as we sent Morse code, so we knew that there was some output. Thing is, the dummy loads did have some wire in it, and they did radiate a bit. And I know I had some local QSOs with or contacts with people on the dummy load, and I think somebody managed to bounce over the Atlantic with it.
Oh, wow.
There you go.
Oh, well. Okay, so that's what a dummy load is. It's you use it just to test your transmitter.
Yeah, and
Okay.
you can't transmit without an antenna hooked up. If you just say, well, I don't want to I just want to, test and make sure that whatever, if you want to hook your antenna and you transmit, you can do damage to your radio. So that's why you need to have a dummy load.
Now, do you buy those, or do you like make those?
You can make them. I bought mine. I bought mine at a swap meet. It was used. It was someone else's, and they were getting rid of it. So, but yeah, you can make one because you
the
see.
critical thing is finding a 50 ohm resistor, because most of them of that power are windings of wire, of resistive wire, and that's not good for radio waves. So to find something like that, you'd probably have to pay more than MFJ sells them for. That's probably, what do you think? It's probably around $150 nowadays. I know that there are some lower powered ones built into some antenna transmatches that some of the companies sell. But
Oh.
you can't run them too long.
Now, Jerry and Bob, the question that I would have, because I don't know this answer, just for, again, practicality's sake, why can't I just turn my power all the way down and be on a frequency where no one is and test?
You can't.
Why do I need to go to a dummy load? Why do I need to spend $150 on a dummy load?
Your antennas, your transmitter is going to work differently when running 5 watts versus 100 watts. And I found that out. I have a manual antenna tuner or transmatch for my ladder line. And if I'm running 5 watts and make my adjustments, fine, it works fine. If I increase it up to 100 watts, I find that I have to readjust.
Oh.
Yeah. And like I bought my dummy load, I bought it at a swap. I think I paid $20 for it. And it came with the oil in it and everything. So
yeah.
Okay.
Don't buy real old ones. They may have bad stuff in the oil, unsafe stuff in the oil.
Oh.
So anything before 1970.
Okay. All right. Hey, let's finish up chapter 4, practical antennas. Now, Jerry started talking about the dipole. That's cool. And it's kind of the basic antenna. Very, very, very common. Some people swear by them. Okay. Now, what it is it's basically a half wavelength of wire cut in the middle, joined with an insulator, and then stretched out. Now, to get the length of wire that you need, well, they say that the calculation is 468 divided by the frequency in megahertz. But later on, and I think the book also said that, it said, it's easier to shorten a wire than it is to lengthen it. So really don't start with 468. Start with a number 490 or some such thing. Because again, it's easier to shorten than it is to lengthen. Now, the dipole, look at the bottom here, the bottom figure B. Okay, what this is showing you is that the dipole radiates off the sides, not off the ends. It radiates off the sides. So, you know, if you've got one end staked to north and one end staked to south, well, then you're not shooting north and south, you're shooting east and west. All right, because you're shooting off the horizontal sides. The top figure A diagram, and again, that's an azimuthal diagram. It's showing you that, you know, you get radiation going in both directions off the sides, okay? Okay, and half a dipole, a quarter of a wavelength, oriented perpendicular to the ground. To a ground plane that acts as an electrical mirror, blah, blah, okay? What they're saying there is that you can build it in such a way that the ground replaces part of the dipole. That is the ground plane antenna. The interesting thing about the ground plane antenna, it's usually used for higher frequencies. Yeah, like Mike's there. They're used for higher frequencies, so we're not talking about, you know, the 80-meter dipole that's, you know, dozens of feet long. You know, we're talking about, you know,
Like 64 feet long.
Yeah.
Yeah. Okay. So, but there's the rubber ducky. Your first radio is probably going to come equipped with this nice rubber ducky antenna. It looks like this. This is the one that came with my radio, with my Yaesu radio. I replaced it with an aftermarket, but when I bought it, it just came like this. All right, so that's the rubber ducky. They're fun to play with. They're not terribly efficient, but it's what everyone starts with. So,
Bob, I have one that's 4 inches tall.
4 inches. Okay.
Talk about efficiency.
Oh, well, this one is what? This one's about about not quite 8 inches. This is not quite 8 inches, but my aftermarket can go up, you know, to 5/8 wavelength for a 2 meter. So
You're going to poke your eye out.
yes, I know.
No, not with that one. That's a poke someone else's eye out.
Oh. Okay, so that's the rubber ducky. Convenient, rugged, yeah. Yeah, it doesn't work well inside of a vehicle, right? Because the metal vehicle, are Corvettes still made out of plastic? Or
Yep.
yeah,
Yep.
okay. So apparently you can do it inside a Corvette, but for those of us with metal vehicles, you know, it's not going to work in a metal vehicle. Okay. For that, if you're using your handheld in a vehicle, you'd actually want something like this, a magnetic mounted antenna that you'd put on your roof, and then lead the cable into the passenger area of the car.
Or
Bobby,
you just
you
roll down,
wanna
roll
show that
down your
again?
window and let the antenna hang out your window.
Bob, you want to pull that out again? I want to illustrate one thing there.
Oh, I bet you're going to talk about the coil, aren't you?
I'm going to talk about that coil.
There you go.
Okay, it's a trap.
It's a trap. It's a
Remember,
trap.
we were talking about capacitance and inductances, and how you get a resonant frequency that can block things. All right, go from the base to the coil. If you can show me the base of the coil. Okay, that base to the coil is probably a quarter wave on 440 megahertz.
Which is 70 centimeter.
70 centimeters. if you're operating a transceiver on 70 centimeters, that trap is going to keep the 70 centimeters just to that part of the antenna. It's only going to allow that length of the antenna, which is the resonance length. If you're operating on 2 meters, then that trap is not going to exist, and it will use the whole length of the antenna. So that's a 2-bander.
Yes. Yes.
And just to throw it out there, I have made this, I don't have it handily available right now, but I have made this kind of ground plane antenna with that coil in it to make it 70 centimeter and 2 meter. You know, so you can still make that too, which is so cool.
Yeah,
So fun.
you have your basement workshop, you can advertise and make $1 million.
Yeah.
So does that coil sort of so you don't have to have like as high of a cable? Does the coil sort of still the same length of the antenna that you would need for the frequency that you're
No,
looking
it's
to
still-
or the wavelength?
It's still got to be the same length for 2 meter.
Okay.
What it's doing is it's just stopping the signal for 70 centimeter. It's saying, nope, I'm stopping at that coil right there. I don't need to go any further when I'm in the 440 range.
Okay.
So yeah, your length of your antenna doesn't really change at all. It's still going to be the same length.
Yeah, now in HF there are ways that you can use inductors to shorten the required length. That's used a lot on vertical antennas for HF, you know, for the 20 meter, 40 meter band, and 80 meter band for that matter. But here it's just that little coil here is only to separate 440 from the 2 meter band.
Yeah.
Okay. Dipole construction. Yes, now here we go. Start with excess length, 490 divided by the frequency in megahertz. Okay. And what this shows is that, you know, you've got a quarter wavelength here, which is terminated in an insulator, and another quarter wavelength over here, also terminated at the insulator. The coaxial cable comes up here. The center connector is connected to one side, and the braid is connected to the other side. Okay.
Now, there are some very neat things that are being sold. Mike, what's the name of that electronics store in Roseville? There's a big radio. They sell mostly CB and a lot of hardware and stuff like that.
If you're
But I got-
asking me, I don't know, because I've been looking for a good electronic store.
Oh, it's there. Okay, I'll find it and let you know. But you can get the ends insulators, and there's some really neat center insulators. Some even accept coaxial cable, and some of them have balance. We haven't really talked about balance and unans and stuff like that yet. But you know, you got the money, they have a place to throw it.
Such is life, huh?
Yeah.
Okay. Ground plane construction. All right. Now this is what Mike was doing. He was making ground plane antenna. So it's 234 divided by the frequency in megahertz. Often short, start long and trim. Okay. The thickness of the whipper rod also affects calculated length, and that is beyond my pay grade. But
Well, the higher the larger diameter, the broader band it is. So
Okay.
the SWR is constant all the way over through the 4 megahertz of 2 meters if
Yeah.
it's broad enough.
Okay. These and these ground plane antennas, you know, they're vertical ground planes. They're omnidirectional. Normally, you mount the whip on the roof of your car or the trunk, assuming your car is metal. Okay. What are we talking about here? Lengthening a quarter wave VHF ground plane to 5/8 wavelength. 5/8 wavelength gives you more signal toward the horizon. This is what Jerry was saying earlier. I don't think I have a graphic for this, but you're going up to 5/8 wavelength instead of just a quarter wavelength. What that does is it flattens out the radiation pattern. So you get less going up and more power pushed out to the side, which is where you want it to go. Okay. And HF vertical antenna size is quite large. Yeah, it's all right. A 40-meter quarter wave whip is about 32 feet. Okay, and that's interesting. You're probably not going to mount that on a car or a truck because
No,
there are a lot of
it's-
bridges that aren't that high.
But you could put it by your house.
Yeah.
The only
Yes.
the only problem is despite what the antenna companies say, you need radials. And for that 40-meter antenna, you're going to need at least 2 radials 32 feet long. So where to put those? I don't know. I remember some guy actually took out his lawn, put all sorts of wire mesh and stuff over his yard, and then covered it with sod. And he connected that as his ground plane. You can be manic about it.
Wow.
Okay. Now, if you can insert an inductor, you can actually get by with a shorter antenna, because the inductor can substitute for some antenna length. Okay.
Sacrifice a little efficiency, but again, compromise.
Okay, beam antennas. We've talked about these before. Gain improves range. Yes. And we also mentioned that, you know, because of the lobes, there are nulls in the lobe, so it reduces reception in unwanted directions, and reduces interference from other stations. Directional characteristics are the same for receiving as they are for transmitting. Okay, and there's a nice little picture of a Yagi, although I showed you a real Yagi. And there's a much more, I think this is in your book, and it shows you a quad.
Deltas and quads, yeah. Actually, it's been proven. There were arguments over about 30 or 40 years. The quad antenna, the 2-element quad antenna, is just as efficient as a 3-element Yagi.
Okay.
So someone
really?
finally did the test.
Okay. Directional antennas, beam antennas, yes, used for getting long distance. DXing means long distance. Okay. They can be used for VHF and UHF to avoid multipath, or to point your signal. Vertical elements for repeaters or FM simplex contacts. Yeah. Use horizontal elements for okay. There is a question that asks for weak signal communications in the VHF and UHF area. All right, weak signal, they're talking about CW, Morse code, and single sideband. You know, in VHF, a lot of the contacts you're going to do is not single sideband. A lot of them are going to be frequency modulation, just regular FM. But you can get more distance with single sideband, because single sideband is a much narrower signal. So you've got more power going into a much narrower signal. Okay, and then, who was it? Someone came up with that question about about the dish antennas. Yeah, these are directional. You know, it's kind of funny, but your technician license will give you access to all these very high frequency bands. The problem is there's not necessarily a lot of equipment made for these bands. So it's really the very advanced hobbyists that kind of get into this. And practical feed lines, we've talked about this. Oh, keep water out. Yeah, obvious, you know. Yeah.
There are some people who have said, "Oh my, for some reason or other, my SWR has gone down to 1:1," and later it's found that there was a gash in the coaxial cable, and rain got in, and so it gave you a very deceptive reading.
Okay. All right. Yeah. They also mentioned this. Some cable is UV rated. Yeah. If your cable is gonna be outside and in the sunlight, yeah, you need to make sure that it can stand up to the elements out there.
And they have some that's built for burial too.
Yeah.
Dig a trench instead of having to go through extraordinary lengths with PVC and stuff like that.
Okay, common coaxial cable. We've talked about this before. We've kind of, you know, spoiler alert, right?
That
Okay.
174 is probably the one you'll see on most of those mag mount antennas, and it's very, very inefficient. But for 10 or 15 feet, you can't beat it for getting it into a car.
Yeah. Okay. All right, connectors. Yes, connectors. Okay, here's the deal. There's these connectors that are, for whatever reason, referred to as UHF connectors, also called SO235 or 239, which SO239 is the receiving part. Okay, that's the receiving part. And the PL259 is the inserting part. Okay, so that's when they say SO239, that's this. PL259, that's this. And the funny thing is that it's called UHF, although it is the most common sized used on HF. In fact, all the way up to 2 meters, all the way up to the 2 meter band, this is the most common link. Then there's this one, BNC connectors, and BNC connectors. The BNC stands, I forget exactly. It's named for 3 guys, Bannett, Neal, and Connor or something. I forget who the C was, but it's 3 guys' names. That's the kind of connection you're going to see on a lot of your handhelds, and it's
a lot of the old computers had computer networking had that kind of connector as well.
Yeah, yeah.
Beat me to it. I was
very easy to use.
There you go, Chris. Yeah.
Okay, and then what's next? SMA connectors. Yeah, I don't see that a lot. SMA stands for sub miniature. I forget what the A stands for, but I don't know. Yeah,
aren't those the ones that are used with most of the Chinese transceivers, the HTs and stuff like that?
Oh, I don't know. I don't know.
The problem is, when I send out my whatever young ham should know, you have to make sure that the antenna you buy, if you're going to buy a 5/8 or something like that, that the connector will plug into your your HT, because some have male, some have female sockets and all that sort of stuff. So be very careful when you're buying something mail order.
Okay, and then these N-type connectors, you'll find these in the very higher frequencies, UHF and above. Okay.
They're very heavy duty.
And then, of course, you've got a whole series of connectors, like there's some connectors that connects the UHF to the BNC, BNC to ends. You know, it's like, I tell you what, you can never have too many connectors.
Amen to that one.
Yeah.
Well,
Okay.
Yeah,
And,
sometimes they try to escape out my drawer.
yeah. Okay. Um, all right, soldering. Rosin core solder. Use rosin core solder. Avoid cold solder. You see what we mean by the subject matter is a mile wide and only an inch deep? That's exactly all we're going to tell you about soldering, except not to use
Acid,
acid core solder.
that's the
Okay.
plumbers.
Yeah. Okay. Rosin core solder. Avoid the cold solder joints, which are joints that what they end up looking not shiny or grainy. Okay. You can find out lots more about soldering on the AAR website. Crimp connectors are becoming more widely used. The tools that go along with it will cost you a little more money, but what the heck? All right, waterproofing. The N-type connectors must be waterproofed. Okay. Use good quality electrical tape and then a layer of self-vulcanizing tape. All righty, I'll do that. Okay, AirCore coaxial cable requires special connections. Yeah, AirCore, that's cable that's got, airspace in it, and you certainly don't want that getting waterlogged.
No one here can afford it.
Okay.
Yeah, that's for darn sure.
All right. Now what? Open feed lines? Yeah. All they're telling you is stuff that's kind of obvious. You keep flexing wire, eventually it'll break. Yes, of course, it's if you're running open a twin lead or ladder line, it's got a very thin plastic coating, and yeah, twisting or abrasion can damage it. Rain, snow, and ice do affect lines, all right? And lower loss than coaxial. This is open wire feed line. Lower loss than coax generally, but of course it's a little more difficult to use. And the fact that it's higher impedance, coax is usually going to be 50 ohms or 75 ohms, whereas open wire lines, ladder line or twin lead is going to be 300 or 450 ohms. And that takes a little work. Okay. Feed line equipment, watt meters, SWR meters. All right. Watt meters. Watt meters are directional things. Now, you may say that the first thing to know about watt meters these days is that, I've got this nice SWR meter, but it has this nice switch right here. If I don't want to measure, I measure SWR that way, but if I want to measure directional watts, I can flip it over to the correct setting. This setting will measure forward wattage, and the next one will measure reflected. Okay. That's for those of you who are particularly sophisticated. I only use mine for SWR. Okay. Directional watt meters. Directional watt meters, yeah, they're sensitive to direction of power flow. Yeah, that's their purpose. Okay. You can either read forward power or reflected power. And SWR is computed from those values, right? Of course, you got to use a table or a formula, or you can just use the SWR meter. And, those things are not expensive. Again, I bought mine at a swap meet, and I think I paid $50 for it. It's okay, easy. All right. What the SWR meter does, it measures standing wave ratio directly by sensing the power flow in the lines, and it's usually installed at the transmitter. And antenna tuners, again, now what we said about antenna tuners is when you have this mismatch It's not good. And the danger is the power going back into your receiver, which you don't want. Normally, you put an antenna tuner at your receiver. If you're using an SWR meter also, it would be your receiver, then your SWR meter, and then your antenna tuner. And what the antenna tuner does is it just provides some additional circuitry with inductors and capacitors, and it just matches the impedance, which goes back to your receiver. Again, it doesn't tune the antenna. They're called antenna tuners, but it doesn't tune the antenna. Okay. All right. Oh yeah, here's the point. The antenna feed point, and the feed point, remember, that's where your coax ties up to your antenna. The impedance mismatch there is not changed. It's still an issue. It's just that the reflected power is not going to hurt your receiver. Okay,
Yeah.
yes, and they're also called impedance matches or trans matches, or I've never heard anyone refer to it as a matchbox. Never ever.
Johnson Matchbox, 1950s.
Oh, okay, 1950s. I
Okay.
remember the 1950s. That was a very nice decade.
Yes, it was very manual though.
Yeah.
Bob, if I can mention that with most modern HF transceivers have a built-in antenna tuner.
Yep.
You will usually handle a mild mismatch of up to about 3-to-1, which is not, if you're going to have a multi-band antenna or an end-fed dipole or something like that, that's going to not do the ticket. So usually if someone buys a modern transceiver, they will also buy an automatic transmatch made by the LDG Corporation that can handle a 10-to-1 mismatch, and that should take care of just about everything.
Okay.
That's about $200.
Okay. Now, what this slide is talking about, is talking actually about a manual antenna tuner, but where you have to adjust your impedances, both your capacitance and your inductance and whatnot. But if you're going to get an antenna tuner, get an automatic one, and you don't have to worry about that. Okay. Antenna analyzers. Oh, these are fun things. These are very cool devices. Here's what one looks like. This is a nice one made by, this is a Rig Expert. It's made by a nice Ukrainian company. And what this does is you can hook your feed line into this, and it will measure your SWR, or there's different settings if you want to measure forward power or reflected power or whatever. But very, very handy. You're probably, that's not a piece of equipment you're going to buy right away. You don't need to. When you first start out, if you need an antenna tuner, borrow one from someone in the local radio club, because they're a few $100, and it's the kind of thing that if you're installing permanent antennas, you'll only need it for a little while, and then because you set up your antenna, you get it tuned, and then you just let it go, and then from time to time you're going to have to check your SWR to make sure things haven't changed. And then, of course, anytime you replace equipment, you're going to want to check with your antenna analyzer also. Okay, the antenna analyzers, yeah, you see, they have a low power signal in them and a frequency counter, and that's how they can tell you how your antenna is performing. That makes antenna and cable measurements, yes, without transmitting at full power. You can get them through through UHF and VHF. When you get the basic models will be HF. If you're getting an antenna analyzer that's going up to UHF, you're going to pay a little bit more money. Yeah, and it's very handy for adjusting troubleshooting antenna and feed lines, and that's wow.
Yeah, let me throw one.
Oh
one
my
thing
God,
out there.
it's 9 o'clock already.
Oh,
I can't-
wow. Let me just throw one quick thing out there, Bob, that antenna analyzer you have, I was looking at that also. They're like, like, I think you said they're like $300 or $400 or something like that. Something that else you can use that is, I've heard just as good. I've never used what you have. I've only looked at it and read about it. I have a Nano VNA.
Yes.
Which only cost $100, and it really does the trick for me. And it, from what I've read, it's very similar, does the similar job. But not as easy to use.
Yeah, a little
Very steep
learning
learning
curve,
curve.
but yeah, Len 88FK chided me about that. We had in that antenna build out at his place. I brought my antenna analyzer and he uses the Nano, and and he pointed out, hey, you've got a really nice antenna analyzer. What did it cost? I told him, well, I don't know what it was, $350 or something, and his.
You have to keep calibrating it and,
Yeah. Every time I use it, I have to recalibrate it, which only
Yeah.
takes 3 or 4 minutes, but you still have to do it every time. I agree. Yep.
for
Okay.
instance, I have an antenna, that's supposed to be multi-band from 6 meters all the way up to 900, from 54 to 900 megahertz, and it can analyze, the VNA can analyze the SWR at each ham band for that antenna. But again, it's an awfully hard. Give it a year or so in the hobby before you start messing with that. You have other stuff you can play with.
So yeah, and this is what the Nano VNA looks like. It's and be careful if you decide, I'm going to get a Nano VNA, make sure you are buying a real Nano VNA as opposed to somebody's off-market brand of a Nano VNA. I made that mistake and I was getting some really funky readings, and then I did some research and found out that what I bought was some off-market brand Nano VNA that had some bad circuitry in it. I then turned around and spent another $100 and got this one.
You bought it from Temu.
And it works great.
Okay.
Okay, and here I made my appearance.
Yes,
All right.
I see.
Hey, there
I
you
put the-
are.
Yeah, I'm gonna go to the store and buy another one of these things and see
Okay.
what's better.
All right. Well, that's it for tonight. So, Jerry, you can take it away on chapter 5 next week.
Okay.
Okay.
What's the best radio?
Yeah, right.
All right. Well,
How
I'm
much
glad
money
to
have
do-
you got? How much money have you got?
Yeah. Yeah, I'm glad that we're all on Zoom, so we don't have any fist fights.
Yeah, that question's as loaded as what kind, should I use a ground plane antenna or should I use something else?
Exactly.
Hey, that's a loaded question, Jeremy. It's got as many answers as there are ham radio operators.
Two hams, 60 answers.
Yep, absolutely.
Okay.
Great. Good job, Bob.
Okay. Well, everyone, thank you for attending, and we'll see you next week.
Thanks.
Take care, everybody.